All right. You see that this is collaborative work from Austrian institutions. It's in fact all Austrian technical universities. I myself, I'm from the Austrian Institute of Technology, which is just roughly 1 hour drive from here, just across the border to Austria. All right, today I will talk about the microstructure evolution of a novel alloy, that is aluminium, 7 magnesium, 3 silicon, 1.5 zinc, and some manganese. But I will start with introducing the technology. Wire arc additive manufacturing, most of you know plots similar like that. I will just quickly go through that. I believe most of the talks we hear are probably in this region of this plot, and today I will focus on this region. So wire DED is the technology for large structures. We're talking about several centimeters to meters with several kilograms per hour deposition rate. The process we are mainly using is the cold metal transfer process. It uses an electrode that is consumable, but it is not just depositing by the motion of the droplet, but also by the motion of the wire itself. You will see that on the next slide. The high deposition rates I already mentioned, with good material efficiency in comparison to subtractive process. It is of course not as material efficient as powder-based processes. We have short lead times and in fact can use all materials that are weldable. The building space we have available for if we use aluminum is nearly unlimited, just limited by the handling system itself. So the robot can reach several meters, and the dimensions, typical dimension and precision is in the range of several millimeters. For generating more complex structures, one can use a CAD/CAM interface. So this is a video. Can you maybe start the video? Sorry, can you start the video? Just click on it. Yeah. So this is a video of the process itself. You see the consumable electrode. Here is the gas nozzle. The melt pool. So we are moving from the right to the left. In the back of the melt pool, you see solidifications starting. And here, the mechanical deposition of the process takes place. This repetitive motion happens with 70 Hertz. At the light metals technology Röhrenshofen, this is one of the 2 workspaces you see that we have available. We're using ABB robots and KUKA robotic systems together with different current sources. Can be, as I said, CMT from Fronius or CMT Twin. We also have the Magic Wave system, which is a TIG system. And we have a plasma welding system from SPI. This forms our equipment for the processing of the light metal alloys. Next, I'd like to talk about the specifics of the alloy development. Most of the literature you find in the field is on commercial alloys. And the reason for that is that having a wire of a new alloy composition, creating it is relatively complex. So we have set up a lab scale process that allows us to manufacture wires ourselves. For this purpose, we typically start in the design alloy design for particular applications. We use one of our casting facilities available, which are in the semi-industrial scale, so we can go up to several tons of alloys. We use wire production, wire hot extrusion, and afterwards we can do the welding one with the wires alongside characterization of the material. What you see here is the result of that extrusion process. We can use spools. They look similar like commercial wires. In this case, we manufacture 4 strands at the time, and the finished product looks like this. And from the surface, it often surpasses the quality of drawn wires. Typical batch sizes of these alloys are for us 0 to 30 kilograms. If we require larger amounts, we collaborate with industrial partners. And now I will come to the part of my talk where I'd like to show you a case study, an example of an alloy that we have developed recently. We have used the processing conditions shown on the left-hand side with simple wall structures shown on the right-hand side. Important is maybe that we used CMT with wire diameter 1.6 millimeter, and the deposition rate was approximately 1 kilogram per hour. Here you can see the chemical analysis of the wire and the deposit. First of all, to the chemical composition itself, we use the combination of magnesium, silicon, and manganese, as this corresponds to a typical high-pressure die casting alloy. We've experienced that alloys made for powder bed processing are less suitable for wire-based processes for several reasons. Nearly all of them are manufacturable, but the problem is that we do not reach the mechanical properties of the powder-based process, as we do not reach these very high cooling rates. Cooling rates are typically in the range of 50 to 100 Kelvin per second, which is more related to the process of high-pressure die casting. Of course, we have repetitive reheating, but the initial cooling is similar to the casting process. So we've started with this alloy, but for precipitation and solution strengthening, we have added additional zinc that is not added to the high-pressure die casting alloy usually. Yeah, the chemical analysis shows that there is a minor loss in magnesium and maybe also in zinc, but more or less the chemical composition remains equivalent. We have also used thermodynamic analysis to understand what is really happening in this alloy. This plot is the phase fraction diagram generated with mud calc, and you see that the major part of the solidification occurs via a eutectic reaction, and thereafter only at below 300 degrees C, the precipitation of T phase or a kind of Laves phase can occur. So we believe that it's actually T phase forming, but the thermodynamic prediction shows similar free energies for both phases. Okay, now let's come to some characterization results. First of all, this is the result of optical light microscopy after a color etching. This is Barker etching, comparing the microstructure of the first layer and the 44th layer, we see relatively little differences. So in gray, you see the eutectic between the dendritically solidified aluminum. Using the SCM, we can shed a little bit more light on what is really happening in the microstructure. As I said before, we have dendrites forming first during solidification, and then subsequently the eutectic reaction. The bright phases you see here are usually intermetallic phases forming with manganese and iron. But also on this scale, we do not see a difference between the topmost layer and layers that were deposited later on. However, we see a difference in the hardness plot. So this was measured in the as-built material condition along the specimen height and plotted as a function of the distance from the substrate. We see early on some influence of the substrate itself, then equivalent hardness values, and in the topmost layers an increased hardness, which is either from solid solution where no precipitates have formed yet, or the precipitates are in a more favorable size range than below due to overaging of the subsequent layers. The aim of this work was also to get an alloy that doesn't require a solution heat treatment, because we want to avoid the distortions that go along with the solution heat treatment, or if you think of very large structures, it can be very difficult to heat treat them at all. So we used DSC to understand the precipitation behavior. Here shown are two experiments. The first is a heating experiment of the as-deposited material, and the second one is after a solution heat treatment. And what you can see is in the black is experiment number 1. In the range where the thermodynamic prediction predicts precipitation of T phase, we find an exothermic peak, and we do not find this peak in experiment number 2. So this suggests that we can generate an oversaturated material during deposition and achieve an age hardening response only during warm aging. Unfortunately, the aging response is weak, and we see only a slight increase in mechanical properties shown here. This is the as-built properties, and these are the T5 properties, so only artificially aged without a solution heat treatment. You see that there is a weak response in aging, in horizontal direction, also in vertical directions, and very important, we see relatively little anisotropy, just a little bit in the fracture elevation. All right, with this, I'd like to sum up my talk. Just briefly, we have processed a novel alloy system with wires that we fabricated ourselves. We've seen a weak texture and hardly elongated grains, no variation in microstructure on the macro scale, and an age hardening response during artificial aging. and nearly isotropic material behavior. The challenges and open questions for the future remain to increase the strength without significant ductility trade-off, to optimize the heat treatment strategy, and expand the material property catalog. As you've seen, we've only done tensile testing so far. Also, fracture properties will be important for such alloys. Thank you.